Welcome to the Late Lab. I'm very glad you've joined me tonight. Before we get into it, do let me know where you're listening from. Maybe you're already tucked into bed, stretched out on the sofa, travelling somewhere late at night, or simply enjoying a quiet moment while the rest of the world slows down. Wherever you happen to be, make yourself comfortable, settle in, and let your mind wander for a while. And if these slow, sleepy journeys through science are something you enjoy, leaving a like and subscribing is a simple way to help the Late Lab keep growing. If you're already subscribed, thank you for continuing to spend these quiet evenings here. It really does mean a great deal. Tonight's question begins with something that sounds almost impossible. Light has no rest mass. Nothing you could place on a scale, nothing solid flying through space, and yet light can push real objects. It can move microscopic particles, influence dust between the planets, drive specially designed spacecraft, and even help shape the behaviour of enormous stars. So I'll do my best not to let a few massless photons push you too far away from sleep. Although if you do stay awake, at least you'll finally know how something with no rest mass can still give matter a very real shove. So get comfortable and let's begin. If light has no mass, how can it push things? Light seems at first like one of the least substantial things in the universe. You cannot hold a beam of sunlight in your hand. You cannot place it on a set of scales and watch the numbers rise. Light can cross millions of kilometers of empty space without carrying along any visible material, and the particles associated with it, photons, have no rest mass at all. And yet, light can push things. A beam of light striking a mirror produces a tiny force. Sunlight can gradually alter the motion of dust grains between the planets. Carefully arranged laser beams can move microscopic particles in a laboratory. Radiation escaping from extremely luminous stars can push gas outward against gravity, and a sufficiently large reflective sail placed in space can use nothing more than sunlight to change its motion. That sounds strange, because our everyday understanding of pushing is built almost entirely from objects that have mass. If you push open a door, your hand presses against the material of the door. At the microscopic level, electromagnetic interactions between the atoms in your hand and the atoms in the surface prevent the two objects from simply passing through one another. Your muscles supply energy, your hand transfers momentum, and the door begins to move. A football moves because a foot strikes it. A shopping trolley rolls because somebody leans against the handle. A stone changes direction because another object collides with it. In all of these familiar examples, there is something solid on both sides of the interaction. Light seems to break that pattern. Sunlight can travel from the sun across roughly 150 million kilometers of space, reach a thin reflective surface, and exert a small but genuine force upon it. No stream of tiny pieces of solar material needs to cross that distance and physically ram into the surface. The electromagnetic radiation itself is capable of transferring momentum. The pressure created by this transfer is known as radiation pressure. Radiation pressure appears whenever electromagnetic radiation exchanges momentum with matter. Light may be absorbed by a surface, reflected away from it, or scattered in a different direction. In every case, if the momentum carried by the radiation changes, the matter interacting with it must experience a corresponding change in momentum. For ordinary light levels, the effect is extremely small. Near Earth, sunlight arriving above the atmosphere carries roughly 1400 watts of power across each square metre facing directly toward the sun. If that light is completely absorbed, the pressure it produces is only a few millionths of a newton per square metre. That is tiny compared with the pressures we encounter in everyday life. Atmospheric pressure at sea level is more than 100,000 newtons per square metre. The push of sunlight is therefore completely overwhelmed by air pressure, friction, vibration, gravity, and countless other effects around us. You are not going to be knocked backwards when somebody opens the curtains. But a weak force does not mean an unimportant force. If the object being pushed is extremely small, even a tiny amount of transferred momentum may noticeably affect its motion. If the source of light is extremely intense, the force can become much larger. And if a small force continues acting for weeks, months, or years in the near absence of friction, its effects can steadily accumulate. This is why radiation pressure matters in places and situations that feel very different from ordinary human experience. A microscopic particle floating in a laboratory can be manipulated by laser light because its mass is so small. A spacecraft equipped with a large solar sail can gradually accelerate because there is very little resistance in space to erase the effect. Dust grains around a star can have their trajectories altered by the star's radiation, and around exceptionally bright stars, the enormous flow of electromagnetic energy can exert enough outward force to influence gas in the stellar atmosphere. None of this requires light to possess rest mass. That distinction is important. When physicists say that a photon is massless, they mean that its rest mass is zero. A photon cannot be brought to rest and weighed in the same sense as an electron, a proton, or a grain of dust. In a vacuum, photons always travel at the speed of light. But zero rest mass does not mean zero energy. And, crucially, it does not mean zero momentum. That is the part that everyday intuition tends to hide from us. In the physics most familiar from ordinary objects moving at ordinary speeds, momentum is often introduced as mass multiplied by velocity. From that equation alone, it is tempting to reason that if mass is zero, momentum must also be zero. For light, that conclusion is wrong. The familiar expression belongs to the classical description of slow-moving massive objects. It is enormously useful in the world around us, but it is not the complete relationship between energy, mass, and momentum provided by relativity. Light carries energy, and because it carries energy while travelling through space, it also carries momentum. When that momentum is absorbed, redirected, or reflected, some of it can be transferred to matter, and a transfer of momentum is exactly what a push really is. This shifts the question into a more useful form. Instead of asking how something without rest mass can somehow behave as though it secretly has mass, we can ask why nature allows momentum to exist without rest mass in the first place. Once that becomes clear, the strange ability of light to move physical objects stops looking like an exception. The mystery is not really that light can push. The mystery is why we ever expected momentum to require mass at all. For most of human history, the idea of momentum was tied very closely to the idea of mass. That is hardly surprising, because almost everything we push, throw, drop, roll, or collide with in everyday life has mass. In classical mechanics, the relationship is beautifully simple. Momentum equals mass multiplied by velocity. This description is closely associated with the mechanics developed by Isaac Newton in the 17th century, and for ordinary objects moving at ordinary speeds, it works extraordinarily well. A slow-moving truck has a great deal of momentum because it has a great deal of mass. A fast-moving tennis ball has much less mass, but its higher speed gives it more momentum than the same ball sitting motionless on the ground. If either object changes its motion, something must change its momentum. The equation feels so natural that it is easy to turn it into a rule about reality itself. If momentum depends on mass, then surely something with no mass must have no momentum. And that is where the trouble begins. The familiar classical relationship is not wrong, it is simply incomplete. To see why, it helps to separate several ideas that are often casually mixed together. Mass describes an intrinsic property of matter related to its inertia. In modern physics, when we speak simply of the mass of a particle, we usually mean its rest mass, sometimes called invariant mass. An electron has a non-zero rest mass. A proton has a non-zero rest mass. A photon has zero rest mass. Inertia describes resistance to changes in motion. For ordinary objects, inertia is closely tied to mass, which is why heavier objects generally require more force to accelerate by the same amount. Velocity describes both how quickly something is moving and the direction in which it is moving. Energy is another physical quantity altogether. It can appear in many forms, including kinetic energy, thermal energy, chemical energy, gravitational energy, and electromagnetic energy. Momentum is connected to motion, but it is not simply another word for energy, speed, or mass. These quantities interact with one another, yet none of them should be treated as interchangeable. The classical expression for momentum works because Newtonian mechanics is an excellent approximation when speeds are much lower than the speed of light. Cars, falling apples, aircraft, ocean waves, footballs, and even most spacecraft can often be described extremely accurately using Newtonian physics. Light cannot. A photon in a vacuum travels at the speed of light, roughly 300,000 kilometers each second. At that point, the relationships between mass, energy, and momentum must be described using relativity rather than the simpler equations of classical mechanics. This is why taking the classical expression for momentum and simply inserting zero for the mass of a photon leads us in the wrong direction. The equation was never intended to describe a massless particle travelling at the speed of light. There is, however, a principle that survives the transition from Newtonian physics into relativity and quantum physics with remarkable strength. Conservation of momentum. In an isolated system, the total momentum remains constant. Momentum may move from one object to another. It may be shared between several particles. It may be carried by matter or by electromagnetic radiation. But when every part of the system is accounted for, the total momentum before an interaction matches the total momentum afterward. A simple collision makes this easier to picture. Imagine two smooth carts on a nearly frictionless track. One cart rolls toward another that is initially stationary. When they collide, the first cart slows down and the second begins to move. The first cart has lost momentum. The second has gained momentum. Nothing mysterious has been created between them. Momentum has been transferred. The same principle applies if a ball strikes a wall and rebounds. The momentum of the ball changes direction. That change means the wall and ultimately the Earth receive a corresponding amount of momentum in the opposite direction. The effect on Earth is far too small to notice because Earth is enormously massive, but the momentum still has to go somewhere. This gives us a more useful way of thinking about a push. A push is not fundamentally the result of one massive object touching another massive object. A push is associated with a change in momentum. Force can be described as the rate at which momentum changes. Force equals the change in momentum divided by the time over which that change occurs. This definition is more general than the familiar expression involving mass and acceleration, because it remains useful even in situations where mass is not changing in the simple classical way, or where radiation is involved. If an object receives momentum gradually, it experiences a small force over a longer period. If the same amount of momentum is transferred very quickly, the force can be much larger. That is why collisions can feel violent even when they last only a fraction of a second, while a gentle continuous push may barely be noticeable even though it acts for much longer. Once momentum is treated as the central quantity, the question of light becomes far less peculiar. We no longer need to ask how a massless thing somehow imitates the behaviour of a massive object. Instead, we can ask a cleaner question. Does light carry momentum of its own? If it does, then light does not need rest mass in order to push anything. It only needs to arrive carrying momentum and then change that momentum through absorption, reflection, or scattering. The matter it encounters must respond, because momentum is conserved. And long before the modern photon picture was developed, electromagnetic theory was already pointing toward exactly that conclusion. Light was not merely carrying energy through space, it was carrying momentum as well. For a long time, light, electricity, and magnetism were treated as different pieces of nature. Light illuminated the world. Electricity could produce sparks and shocks. Magnets could pull iron across a table without touching it. Each seemed strange in its own way, but there was no obvious reason to believe they were all expressions of the same underlying phenomenon. That began to change during the 19th century. Experiments by scientists including Michael Faraday showed that electricity and magnetism were deeply connected. Changing magnetic conditions could produce electric effects, while electric currents could generate magnetic fields. Then, James Clerk Maxwell brought these ideas together. During the 1860s, Maxwell developed a mathematical theory describing electric fields and magnetic fields as parts of one electromagnetic system. His work did more than organize earlier discoveries. It revealed something unexpected. The equations predicted waves. A changing electric field could be accompanied by a changing magnetic field. That changing magnetic field could in turn be accompanied by another changing electric field. The disturbance could continue through space as a self-propagating electromagnetic wave. When Maxwell calculated how quickly these waves should travel, the result matched the known speed of light. Light, it seemed, was electromagnetic radiation. Visible light was no longer something completely separate from electricity and magnetism. It was one part of a much broader electromagnetic phenomenon. This also changed the way physicists could think about energy. An electromagnetic field is capable of storing energy. A travelling electromagnetic wave can transport that energy from one place to another. Nothing massive has to move from the source all the way to the destination. When sunlight reaches Earth, for example, no ordinary material bridge stretches between the surface of the sun and your window. Electromagnetic radiation crosses the intervening space, carrying energy with it. That alone is remarkable, but Maxwell's theory implied something even more important for the question of how light can push. Electromagnetic radiation carries momentum as well. This was already present in classical electromagnetic theory, long before physicists began speaking about photons in the modern quantum sense. If an electromagnetic wave carries momentum, then when the wave interacts with matter, some of that momentum can be transferred. That transfer produces radiation pressure. In the classical field description, there is no need to imagine light as a stream of tiny solid pellets striking a surface one after another. Instead, an electromagnetic wave reaches matter, interacts with the charged particles inside it, and changes the motion of those charges. Matter is full of electrically charged constituents. electrons carry negative electric charge, while atomic nuclei contain positively charged protons. When the electric field of an incoming electromagnetic wave reaches a material, it can exert forces on these charged particles. The charges respond to the field. Depending on the material and the frequency of the radiation, electrons may shift slightly, oscillate, absorb energy, or contribute to radiation being reflected or scattered. The magnetic part of the electromagnetic wave also participates in the interaction. Moving charges respond to magnetic fields, and the combined electric and magnetic forces account for the transfer of momentum between the field and the material. The details can become mathematically sophisticated, but the physical idea is wonderfully simple. The electromagnetic field arrives carrying momentum. Its interaction with matter changes how that momentum is distributed. The matter therefore experiences a force. This gives the electromagnetic field a very physical role. It is not merely a mathematical label placed over an interaction between distant objects. The field can contain energy, transport energy, carry momentum, and deliver that momentum somewhere else. The Sun provides an enormous natural demonstration. Earth orbits at an average distance of roughly 150 million kilometers from the Sun. Astronomers call this average distance 1 astronomical unit. Most of the region between the Sun and Earth is extraordinarily empty compared with the environments familiar to us on the ground. Yet every second, electromagnetic radiation crosses that distance and reaches Earth. Sunlight warms the oceans and continents. It powers photosynthesis. It drives much of Earth's weather. And because that same radiation carries momentum, it also exerts pressure on whatever absorbs, reflects, or scatters it. The pressure is extremely small under ordinary conditions, but its existence matters. A perfectly absorbing surface facing sunlight near Earth's orbit experiences a radiation pressure of only a few millionths of a Newton across each square meter. A strongly reflecting surface can experience roughly twice the pressure because the outgoing light reverses much of its momentum. Those forces sound almost laughably small beside the forces of everyday life. But physics does not require a force to be large before it becomes real. In space, where friction can be negligible and an object may remain exposed to sunlight for months or years, even a tiny continuous force can gradually alter motion. And the key point is that Maxwell's theory already anticipated this. Radiation pressure was not invented later to rescue the idea of photons. Classical electromagnetism itself says that a travelling electromagnetic wave carries energy and momentum, and that changing the momentum of that wave must produce a corresponding effect on matter. The quantum description of light would later reveal that electromagnetic radiation exchanges energy and momentum in discrete interactions. But the ability of light to push does not depend on picturing photons as microscopic billiard balls. Long before quantum mechanics arrived, Maxwell's electromagnetic field had already shown that apparently weightless light could carry something capable of moving the material world. Once light is understood as an electromagnetic wave, another question naturally appears. If energy is travelling through space, can we describe exactly where it is going and how quickly it is moving from one place to another? During the 19th century, the English physicist John Henry Poynting helped provide an answer. Building on the electromagnetic theory developed by James Clerk Maxwell, Poynting studied how energy moves through electric and magnetic fields. His work gave physicists a more concrete way to describe something that might otherwise sound rather abstract. Electromagnetic energy was not simply present somewhere near a source and then mysteriously present somewhere else later. It had a measurable flow through space. The quantity used to describe that flow became known as the Poynting vector. Despite the rather mathematical name, its physical meaning can be understood quite gently. The Poynting vector describes the direction in which electromagnetic energy is flowing and how much energy passes through a given area during a given amount of time. Imagine sunlight streaming through an open window. The light is carrying energy into the room. If you could describe the energy flow at every point in the beam, arrows could be imagined pointing roughly in the direction the light is travelling, with their size representing how strongly energy is flowing there. That is essentially the role played by the Poynting vector. For an electromagnetic wave moving through empty space, the electric field and magnetic field oscillate while energy flows forward through the region. Nothing resembling a stream of conventional matter needs to accompany it. The electromagnetic field itself carries the energy. And wherever electromagnetic energy flows, momentum flows with it. This connection is central to understanding radiation pressure. A beam of light travelling in a particular direction carries momentum in that same general direction. If the beam continues through empty space without encountering anything, its momentum simply continues travelling with it. But when the beam reaches matter, the situation changes. Suppose light falls upon a dark surface and is absorbed. The electromagnetic energy entering the surface no longer continues forward as the same beam. The momentum associated with that radiation has therefore changed. Momentum cannot simply vanish. The combined system consisting of the electromagnetic field and the material must still obey conservation of momentum. If the light loses forward momentum, the material gains corresponding momentum. The surface receives a push. Reflection makes the effect even easier to picture. If light arrives moving toward a mirror and then leaves travelling back in the opposite direction, the momentum carried by the electromagnetic radiation has changed direction. The mirror must receive the balancing change in momentum. This is not merely a useful story told after observing that light can exert force. Maxwell's electromagnetic theory contains the machinery needed to calculate these effects quantitatively. One important part of that machinery is known as the Maxwell stress tensor. The name sounds considerably more intimidating than the basic idea requires. In ordinary materials, the word stress describes internal forces distributed through an object. A stretched rope, a compressed spring, or a loaded beam can all carry mechanical stress. Electromagnetic fields can also carry and transfer something analogous to mechanical stress. The Maxwell stress tensor provides a mathematical description of how electric and magnetic fields transport momentum and exert forces across surfaces and through regions of space. It allows physicists to calculate the forces that electromagnetic fields place on charged matter. There is no need to wander through the full mathematics to appreciate what this means. Radiation pressure is not an approximate metaphor suggesting that light behaves a little bit like something pushing. It is a calculable consequence of electromagnetism. The amount of pressure depends directly on the amount of electromagnetic energy arriving. A brighter beam transports more energy through a given area during each second. Because electromagnetic radiation also carries momentum, that greater energy flow corresponds to a greater momentum flow. More momentum arriving each second means a larger possible force. This is why the intensity of light matters so much. Near Earth's distance from the Sun, the intensity of sunlight above the atmosphere is roughly 1400 watts per square metre on a surface facing the Sun directly. A watt measures energy transferred each second, so every square metre exposed directly to this sunlight receives electromagnetic energy at a rate of roughly 1400 joules each second. That sounds substantial when expressed as energy. The corresponding radiation pressure, however, is surprisingly small. For a surface that perfectly absorbs the sunlight, the pressure is only around 5 millionths of a newton per square metre. A newton is already a fairly modest unit of everyday force. The gravitational force on a small apple near Earth's surface is roughly 1 newton, so spreading only a few millionths of a newton across an entire square metre produces a push far too gentle for a person to notice. If you stood outside in bright sunshine, radiation pressure would technically be pushing you. You would simply have several more urgent forces to worry about, including gravity and the ground politely refusing to let you fall through it. But the smallness of the force can be deceptive. On Earth, friction, air resistance, vibration, and countless other effects overwhelm radiation pressure in most ordinary situations. Space is different. A spacecraft travelling through interplanetary space does not experience anything resembling the constant friction encountered by a car moving through air. If sunlight applies a tiny force to a large reflective surface, that force can continue acting hour after hour and month after month. Acceleration produced during any 1 second may be almost negligible, but acceleration accumulates. A small change in velocity repeated continuously can eventually become a much larger change in motion. The same logic becomes important for extremely small particles. A microscopic object contains so little mass that even the tiny momentum carried by light can become significant compared with the other forces acting upon it. What appears negligible at human scale can therefore become useful in laboratories and influential across astronomical distances. John Henry Poynting's description of electromagnetic energy flow helps reveal why. A beam of light is not merely illuminating the space through which it passes. Energy is flowing. Momentum is flowing with it. And whenever that flow is interrupted, absorbed, redirected, or reflected, the material responsible for changing it must feel the consequences. A prediction becomes much more convincing when nature can be persuaded to reveal it directly. By the end of the 19th century, electromagnetic theory had already provided strong reasons to believe that light should exert pressure. James Clerk Maxwell's equations implied that electromagnetic radiation carries momentum and that changing that momentum should produce a force on matter. The difficulty was not the theory. The difficulty was measuring the effect. Radiation pressure from ordinary light is extraordinarily small, especially compared with the forces that surround us constantly on Earth. A tiny movement caused by light can easily be hidden beneath air currents, thermal expansion, vibration from the floor, convection inside an experiment, or even the faint mechanical disturbances created by nearby equipment. To demonstrate radiation pressure convincingly, physicists needed instruments sensitive enough to detect forces that would normally be completely lost in the background. One of the first successful measurements was carried out by the Russian physicist Pyotr Nikolaevich Lebedev. Around the beginning of the 20th century, Lebedev designed experiments intended to detect the mechanical pressure produced when light struck carefully suspended surfaces. The basic idea was wonderfully direct. If light truly carried momentum, then shining it onto a small surface should exert a force. Attach that surface to an apparatus capable of twisting or rotating by an extremely small amount, and the force might become measurable. But in practice, this was anything but simple. Light does more than transfer momentum, it also transfers energy. When a surface absorbs light, it becomes warmer. That heating can create secondary effects. Nearby gas molecules may move differently. One side of an apparatus may expand slightly more than another. Temperature differences can produce tiny air currents or forces that look very much like the signal being sought. even experiments performed at reduced pressure could suffer from residual gas effects. This meant that detecting a movement after shining light on something was not enough. The experiment had to show that the movement came from radiation pressure itself rather than from heating. Lebedev worked to reduce these competing influences and succeeded in obtaining measurements broadly consistent with Maxwell's theoretical prediction. At around the same period, two American physicists, Ernest Fox Nichols and Gordon Ferry Hull, carried out their own experiments. Nichols and Hull used extremely sensitive torsion-based apparatus to measure the force exerted by radiation. A torsion system works by allowing a suspended component to twist by a minute amount. If the restoring force of the suspension is known, an exceptionally small torque can be inferred from the amount of rotation. This turns an almost unimaginably weak push into something that can, with sufficient care, be measured. Their experiments were performed under conditions designed to suppress thermal disturbances as much as possible. Reflecting surfaces could be exposed to radiation, while unwanted heating effects were carefully studied and controlled. The results again supported the electromagnetic prediction. Light really did exert mechanical pressure. That distinction matters. A surface becoming warmer when illuminated is familiar. Leave a dark object in sunlight, and its temperature rises because electromagnetic energy is being absorbed. But heating and radiation pressure are not the same physical effect. Heating concerns the transfer of energy into microscopic degrees of freedom within matter. Atoms vibrate more strongly, molecules move more energetically, and the internal energy of the material increases. Radiation pressure concerns momentum. The two can occur together, because the same incoming radiation carries both energy and momentum. Imagine light being completely absorbed by a surface. Its energy enters the material and may eventually become heat. At the same time, the forward momentum carried by that radiation must be transferred. The object therefore receives a tiny push. If the radiation is reflected instead, the momentum transfer can be even greater because the light leaves travelling in a different direction. This was precisely what electromagnetic theory said should happen. The early radiation pressure experiments were important because they showed that this was not merely a mathematical curiosity hidden inside Maxwell's equations. Electromagnetic radiation could produce an observable mechanical effect. Light could move matter, and the measured forces were of the scale expected from the amount of energy and momentum carried by the radiation. There was something rather satisfying about this result. A beam that appears almost ghost-like to human senses, capable of crossing a room without disturbing the air in any obvious way, was shown to be carrying something physically transferable. The push was tiny, but it was real. Yet these experiments were taking place during an extraordinary period in physics, because at almost exactly the same time, the classical understanding of light was beginning to encounter serious problems elsewhere. Maxwell's electromagnetic wave theory was enormously successful. It explained interference, diffraction, polarization, and the propagation of electromagnetic radiation. It correctly predicted that light could carry energy and momentum, but certain interactions between light and matter refused to fit comfortably within a purely classical picture. Max Carl Ernst Ludwig Planck had already been forced to introduce discrete quantities of energy while studying thermal radiation. Then, Albert Einstein would take an even more radical step when thinking about the photoelectric effect. The electromagnetic field would not disappear from physics. Quite the opposite. It would remain fundamental. But the way energy and momentum were exchanged between radiation and matter would acquire a quantum description. Light could behave in ways that could not be captured simply by imagining energy spread continuously through a classical wave. Eventually, physicists would describe electromagnetic radiation in terms of photons, each carrying its own energy and momentum. This did not overturn the experiments of Pyotr Nikolaevich Lebedev, Ernest Fox Nichols, or Gordon Ferry Hull. It deepened their meaning. Classical electromagnetism had correctly predicted that radiation carries momentum and therefore exerts pressure. Quantum physics would reveal how that momentum appears in individual interactions. The push of light had been measured. The next mystery was understanding what, exactly, was doing the pushing. By the beginning of the 20th century, light had already acquired an impressive description. James Clerk Maxwell had shown that it could be understood as an electromagnetic wave. Those waves could carry energy through empty space, and the theory correctly predicted that they also carried momentum. Experiments had even begun measuring the faint pressure that radiation exerted on matter, and yet something about light was still missing. The first major clue emerged from the work of Max Carl Ernst Ludwig Planck. In 1900, Planck was studying the spectrum of radiation emitted by heated objects. Classical physics struggled to reproduce the observed distribution of energy across different frequencies. To obtain the correct result, Planck introduced a strange assumption. Energy could be exchanged in discrete amounts. The size of each amount depended on the frequency of the radiation. The relationship can be expressed as energy equals Planck's constant multiplied by frequency. This meant that higher frequency radiation was associated with larger individual quantities of energy, while lower frequency radiation was associated with smaller ones. Planck initially treated quantization with considerable caution, but the idea opened a door that physics would never quite manage to close again. Albert Einstein pushed the concept much further. In 1905, Einstein examined the photoelectric effect, in which light striking certain materials can cause electrons to be emitted from their surfaces. Some of the experimental behaviour was difficult to understand if light delivered its energy only as a smoothly distributed classical wave. Increasing the brightness of light below a certain frequency did not necessarily release electrons, but radiation above the required frequency could do so, even when the light was relatively faint. Einstein proposed that light itself behaved during these interactions as though its energy were concentrated into individual quantities. Each quantum of light carried energy determined by its frequency. Higher frequency light therefore delivered more energy in each individual interaction. These light quanta eventually became known as photons. This does not mean that a photon should be imagined too literally as a tiny glowing marble racing through space. That picture can occasionally be useful, but it becomes misleading very quickly. In modern quantum electrodynamics, a photon is understood as a quantum excitation of the electromagnetic field. The electromagnetic field remains fundamental. What quantum theory changes is the way that field exchanges energy and momentum with other quantum systems, and momentum is where the connection to pushing becomes especially important. A photon has zero rest mass, but it does not have zero energy, and because it has energy, it also carries momentum. For light travelling through empty space, the relationship is remarkably simple. Photon momentum equals photon energy divided by the speed of light. So a photon with more energy also carries more momentum. Because photon energy increases with frequency, higher frequency photons carry more momentum individually than lower frequency photons. Equivalently, shorter wavelength photons carry more momentum than longer wavelength photons. None of this requires the photon to possess hidden rest mass. The phrase rest mass is important because mass and energy are related without being identical. An electron has rest mass. It can, at least in principle, be considered in a frame where it is stationary. Additional energy can then be given to it, increasing its motion. A photon is fundamentally different. There is no valid rest frame for a photon. In vacuum, light travels at the speed of light, roughly 300,000 kilometers each second. A photon is not an object that begins stationary, accelerates through a sequence of slower speeds, and eventually reaches that value. Massless excitations such as photons propagate at the invariant speed of relativity in vacuum. That is why trying to understand them by taking the ordinary mechanics of a moving ball and simply setting its mass to zero creates so much confusion. Photons belong to a different relativistic situation. Interestingly, the quantum description does not destroy Maxwell's earlier picture of radiation pressure. The two descriptions agree. A classical electromagnetic wave carries a continuous flow of energy and momentum. In the quantum description, electromagnetic radiation exchanges energy and momentum through photon interactions. If a large number of photons strike an absorbing surface, their individual momentum transfers add together. The result, averaged across enormous numbers of interactions, is the same radiation pressure predicted by classical electromagnetism. If the photons are reflected, their momentum changes direction, and the surface receives a larger momentum transfer. If they scatter, the change in their outgoing momentum is balanced by a corresponding change in the material with which they interacted. At large scales, where unimaginably many photons are involved, the smooth electromagnetic wave description can work beautifully. At the scale of individual interactions between light and matter, the quantum description becomes essential. They are not competing explanations in which one says light is a wave and the other insists it is secretly a collection of ordinary particles. They are parts of the modern description of the electromagnetic field. And this finally brings the apparent contradiction into sharper focus. Calling a photon massless tells us that its rest mass is zero. It does not tell us that its energy is zero. It does not tell us that its momentum is zero. And it certainly does not mean that it is incapable of changing the motion of matter. The deeper reason becomes clear only when the classical expression for momentum is replaced by the relativistic relationship between energy, momentum, and rest mass. There, momentum without rest mass is not an exception that physics has to explain away. For light, it is exactly what the mathematics requires. The final piece of the puzzle comes from relativity. For objects moving at ordinary speeds, Isaac Newton's description of momentum works so well that there is rarely any reason to question it. A moving object has mass, it has velocity, and together those quantities determine its momentum. But light does not belong to that ordinary world. A photon travels through vacuum at the speed of light, roughly 300,000 kilometers each second. At such an extreme speed, the familiar Newtonian relationships between mass, motion, energy, and momentum are no longer complete. Albert Einstein's special theory of relativity, introduced in 1905, replaced them with a deeper description. One of the central ideas of special relativity is that the speed of light in vacuum has the same value for every inertial observer, regardless of how the source or observer is moving. Space and time must therefore adjust in ways that ordinary intuition does not anticipate. Time intervals can differ between observers. Lengths measured along the direction of motion can differ. And energy and momentum must be described using relationships that remain consistent for every inertial observer. A few years later, Hermann Minkowski developed a particularly powerful way of expressing Einstein's theory. Minkowski treated space and time as parts of a unified structure known as spacetime. in much the same spirit. Relativity reveals that energy and momentum are not completely separate pieces of bookkeeping. They belong to a unified relativistic description of a physical system. This is where the apparent problem of massless momentum begins to dissolve. For a particle with rest mass, relativity connects its total energy, its momentum, its rest mass, and the speed of light through one fundamental relationship. Written entirely in words, that relationship is energy squared equals momentum squared multiplied by the speed of light squared plus rest mass squared multiplied by the speed of light to the fourth power. It looks considerably less frightening when we focus on what it is saying. For a massive particle, some of its energy is associated with its rest mass, while additional energy and momentum are associated with its motion. An electron, for example, has a non-zero rest mass. If it is stationary relative to an observer, it still possesses rest energy. If it begins moving faster, its total energy and momentum increase. A photon is different because its rest mass is exactly zero. And this is the crucial point. Setting the rest mass to zero does not make the entire relativistic relationship collapse to zero. It simply removes the rest mass term. What remains is a direct relationship between energy and momentum. For light in vacuum, photon momentum equals photon energy divided by the speed of light, so a photon can possess zero rest mass while still possessing non-zero momentum, provided that it has non-zero energy. And photons most certainly do have energy. The energy carried by a photon is connected to the frequency of the electromagnetic radiation. Higher frequency light carries more energy in each photon. That means higher energy photons also carry more momentum individually. A gamma-ray photon therefore carries far more momentum than a photon of visible light, while a visible light photon carries more momentum than a much lower frequency radio photon. Assuming we are comparing individual photons, the same relationship can also be expressed through wavelength. Shorter wavelength radiation corresponds to higher frequency, greater photon energy, and therefore greater momentum per photon. This does not mean that a dim beam of high-frequency radiation must always push harder than a bright beam of lower-frequency light. The total force also depends on how many photons arrive, how much total energy reaches the surface, and whether the radiation is absorbed, reflected, or scattered. But on the level of individual photons, greater photon energy means greater photon momentum. This is exactly the kind of relationship that Newtonian mechanics cannot describe properly. If we used only the familiar classical expression involving mass multiplied by velocity, we would set the photon's mass to zero and incorrectly conclude that its momentum must also be zero. Relativity tells us why that reasoning fails. The classical expression is an approximation appropriate for massive objects moving much more slowly than light. A photon is massless and always travels at the invariant speed of light in vacuum. It therefore has to be treated using the relativistic relationship from the beginning. There is also an older piece of terminology that can create unnecessary confusion. Historically, some explanations referred to something called relativistic mass. As an object gained energy through motion, its relativistic mass was said to increase. That language can make it sound as though energy literally turns into additional rest mass simply because an object moves faster. Modern physics usually avoids that convention. Instead, mass normally refers to invariant mass, or rest mass, which does not change merely because an observer sees an object moving faster. Energy and momentum are then treated as separate but related quantities that do depend on the state of motion. This distinction makes photons much easier to understand. A photon does not acquire mass because it is moving quickly. Its rest mass remains zero. Its energy is non-zero. its momentum is non-zero, and those statements are perfectly compatible with one another. The connection to force now becomes almost unavoidable. Imagine a photon travelling toward a surface. Before the interaction, the photon carries momentum in the direction of travel. If the photon is absorbed, that momentum no longer continues forward as part of the incoming photon. Conservation of momentum requires the material to receive the corresponding momentum. If the photon is reflected, its momentum reverses direction, producing an even larger change. If it scatters away at an angle, part of its momentum changes direction, and the material receives the balancing change. Nothing in this process requires the photon to possess rest mass. What matters is that it possesses momentum before the interaction, and that this momentum changes during the interaction. That change is what allows light to exert a force. Relativity therefore removes the contradiction at the heart of the question. Light has no rest mass, but rest mass is not a requirement for momentum. Energy and momentum are woven together more deeply than Newtonian intuition suggests, and a massless photon carrying energy must also carry momentum. So when light pushes a mirror, moves a microscopic particle, or slowly accelerates a spacecraft, it is not behaving as though it secretly had mass all along. It is doing something far more straightforward. It is transferring the momentum that relativity says it was always carrying. The simplest way for light to push something is for the light to arrive and disappear into it. Imagine a beam striking a perfectly dark surface that absorbs every photon reaching it. Nothing is reflected back. Nothing passes through. The incoming light simply transfers its energy into the material. But the energy is not the only thing being transferred. Each incoming photon also carries momentum in the direction in which it is travelling. If the photon is moving toward the surface, then before the interaction there is momentum directed toward that surface. Once the photon has been absorbed, it no longer exists as a freely travelling photon carrying that momentum onward. The momentum cannot simply vanish. Conservation of momentum requires the combined system of the light and the object to preserve the same total momentum before and after the interaction, so the material receives it. That is the push. The important point is that nothing needs to acquire the photon's rest mass, because the photon did not have any rest mass to begin with. What the material receives is energy and momentum. On the microscopic level, absorption can occur in several different ways depending on the material and the frequency of the incoming radiation. An electron inside an atom may absorb energy and move into a higher energy state. In a solid, energy may be transferred into the motion of electrons or into collective vibrations of the atomic lattice. In molecules, absorbed electromagnetic radiation may increase rotational or vibrational motion. Eventually, much of that energy may become thermal energy, spreading through the material as random microscopic motion. This is why a dark surface left in sunlight tends to become warm. But the heating should not be confused with the momentum transfer. They are connected because the incoming radiation carries both energy and momentum, yet they describe different aspects of the interaction. The energy deposited in the material may increase its internal energy. The momentum deposited in the material changes the motion of its centre of mass, even if the resulting movement is far too small to notice. For a large object sitting on Earth, that mechanical effect is almost completely hidden. The object rests against the ground. Friction acts on it. Gravity holds it in place. Air molecules constantly strike it from every direction. The tiny push from absorbed light becomes insignificant beside these much larger influences. But if the same surface were floating freely in space, the situation would be different. each absorbed photon would still deliver only a minute amount of momentum, yet photons would keep arriving. The individual transfers would accumulate into a continuous force. For an ideal surface that absorbs all incoming radiation, the relationship between the intensity of the light and the resulting pressure can be written very simply. Radiation pressure equals light intensity divided by the speed of light. The reason the pressure is so small becomes clear from that expression. The speed of light is enormous. It is roughly 300,000 kilometers each second. So even a substantial flow of electromagnetic energy corresponds to a relatively modest flow of momentum. Consider sunlight near Earth. Above the atmosphere, a surface facing directly toward the sun receives roughly 1400 watts of electromagnetic power across each square meter. For a perfectly absorbing surface, that corresponds to a radiation pressure of roughly 5 millionths of a Newton per square meter. Compared with atmospheric pressure, this is almost absurdly small. At sea level, the atmosphere presses on surfaces with roughly 100,000 newtons per square meter. Sunlight therefore produces a pressure tens of billions of times smaller than ordinary atmospheric pressure. It is no surprise that we do not feel ourselves being pushed noticeably across the pavement on a sunny afternoon. But that small number remains physically real. Sensitive experiments can measure it. Microscopic particles can respond to it. And objects in space can accumulate its effects over long periods. There is another subtlety when absorbed light becomes heat. A warm object usually emits electromagnetic radiation of its own. That outgoing thermal radiation also carries momentum. If the object emits equally in every direction, the various recoils largely cancel one another. But if more thermal radiation escapes from one side than another, the object can experience a small net recoil. This principle appears in real spacecraft dynamics. Uneven thermal radiation can produce tiny forces that gradually alter a spacecraft's motion over long periods. So even after the original photon has been absorbed, momentum accounting continues. Energy may move through the material, become heat, and later leave again as newly emitted radiation. Every outgoing photon carries momentum with it. The complete system must balance all of these exchanges. That is why conservation laws are so powerful. They do not care whether the energy appears as visible light, infrared radiation, microscopic vibration, or motion of the entire object. The bookkeeping still has to work. Absorption, therefore, gives us the cleanest possible example of how massless light produces a force. A photon arrives carrying energy and momentum. The material absorbs it. The energy becomes part of the internal energy of the material in some form, while the photon's forward momentum is transferred to the object. The object's momentum changes, and whenever momentum changes over time, there is a force. Nothing has borrowed mass from the light. Nothing has secretly turned the photon into a tiny conventional projectile. The push appears because momentum itself is being transferred. And if simply stopping the light can push an object, then making the light reverse direction can produce an even larger effect. Absorbing light is enough to produce a push, but reflection can produce an even larger one. The reason comes down to momentum. Imagine a beam of light travelling directly toward a mirror. Before the interaction, the electromagnetic radiation carries momentum in the direction of the mirror. If the light were completely absorbed, that forward momentum would be transferred into the material. The light would stop travelling onward as the original radiation, and the mirror would receive the corresponding change in momentum. Reflection changes the situation. Instead of disappearing into the surface, the light leaves again. and if it reflects straight back, its momentum now points in the opposite direction. That reversal matters. Suppose we imagine the incoming momentum as pointing toward the mirror. After reflection, the outgoing momentum points away from it. The momentum has therefore not merely fallen to zero. It has crossed from one direction to the opposite direction. That produces a larger total change. Conservation of momentum requires the mirror to receive the corresponding difference. So, all else being equal, reflected light can push harder than absorbed light. For an ideal surface struck directly by a beam and reflecting it perfectly back along the incoming direction, the radiation pressure is approximately twice that produced by perfect absorption at the same intensity. In spoken form, the relationship can be written as radiation pressure for perfect reflection equals twice the light intensity divided by the speed of light. This does not mean that reflection somehow creates additional momentum from nowhere. The extra effect comes from the fact that the outgoing light still carries momentum, but now in the opposite direction. Imagine an ordinary ball approaching a wall. If the wall somehow catches the ball and keeps it, the ball goes from having forward momentum to having none. But if the ball rebounds with nearly the same speed, its momentum changes from forward to backward. The total change is larger. A mirror produces an analogous momentum change for light, although individual photons should not be imagined too literally as tiny hardballs striking a polished surface. Quantum mechanically, reflection arises through the interaction of the electromagnetic field with charged particles in the material. The collective response of electrons within the surface produces outgoing electromagnetic radiation in a way that, under the right conditions, forms the reflected beam. At larger scales, however, following the incoming and outgoing momentum gives exactly the right intuition. The light approaches, its momentum changes direction. The mirror receives the balancing momentum. Real mirrors, of course, are not perfect. Some light is reflected, some may be absorbed and converted into internal energy. Some materials allow a portion to pass through. The force on a natural surface, therefore, depends on several properties at once. Reflectivity determines how much radiation leaves in a reflected direction. Absorption determines how much energy and momentum remain within the material. Transmission determines how much continues through the object. The angle at which light strikes the surface also matters, because momentum is a directional quantity. A beam arriving directly perpendicular to a mirror produces a different momentum transfer from one arriving at a shallow angle. The direction in which the outgoing radiation travels must also be taken into account. All of this means that the pressure exerted by real light on real materials is more complicated than the perfectly absorbing or perfectly reflecting cases. Those ideal cases remain useful because they reveal the underlying principle cleanly. Change the momentum of the radiation, and matter must respond. This becomes especially important when engineers want to use light as a source of propulsion. A solar sail is designed to exploit radiation pressure from sunlight. The sail is made extremely large and extremely lightweight, so that a very small force can produce a useful acceleration. High reflectivity is especially valuable. If sunlight were simply absorbed, the sail would still be pushed, but a reflective sail can receive a larger momentum transfer because much of the incoming radiation changes direction rather than simply being absorbed. Reflection also reduces the amount of solar energy converted directly into heat within the sail. That matters because a very thin sail exposed to intense sunlight must remain light without becoming excessively hot or suffering damage. The force involved remains tiny by the standards of ordinary propulsion. A chemical rocket can produce enormous thrust for a relatively short period. sunlight provides something very different. The acceleration can be extremely gentle, but it does not require the spacecraft to burn onboard propellant in order to maintain that particular force. And in space, gentle forces have patience. There is no road surface creating rolling resistance. There is no thick atmosphere constantly slowing the spacecraft down. A small acceleration acting continuously can gradually change the spacecraft's velocity. After 1 second, the difference may be negligible. After 1 hour, it is still modest. But after days, months, or longer, the accumulated effect becomes increasingly important. This is one of the most striking consequences of radiation pressure. A photon has no rest mass. A thin reflective sheet may weigh only a tiny amount compared with an ordinary spacecraft, and yet sunlight travelling across empty interplanetary space can steadily alter that spacecraft's motion. The mirror does not need to be struck by conventional matter. The light does not need to possess hidden mass. What matters is the momentum carried by the radiation before the interaction and the momentum carried away afterward. Absorption transfers forward momentum. Reflection changes the direction of that momentum and can transfer even more. The push is simply the material side of that momentum change. And once light is allowed to leave in directions other than straight backward, the same principle becomes even more versatile, because scattering can transfer momentum in almost any direction. Light does not need to be absorbed or reflected cleanly from a mirror in order to transfer momentum. There is another possibility. It can scatter. Scattering happens when incoming radiation interacts with matter and then leaves in a different direction, sometimes with a different energy as well. The outgoing light may be only slightly redirected, or it may emerge at a completely different angle. In some cases its wavelength changes, in others its energy remains almost the same. But whenever the momentum of the light changes, something else must account for that change. The matter involved in the interaction receives the corresponding momentum. This makes scattering one of the clearest ways to see that the ability of light to push is really about momentum rather than mass. Imagine a photon travelling toward an electron. The photon approaches with a certain energy and a certain momentum. After the interaction, suppose the photon leaves in another direction. Even if its energy stayed exactly the same, changing direction would still mean changing momentum, because momentum includes direction as well as magnitude. The electron must therefore recoil. If the outgoing photon also carries less energy than it did before, its momentum changes even more. The missing energy and momentum are transferred into the motion of the electron. One of the most important demonstrations of this behaviour came from the American physicist Arthur Holly Compton. In 1923, Compton studied the scattering of high-energy electromagnetic radiation from matter. At the time, the nature of light was still at the centre of a major transformation in physics. Classical electromagnetic theory described light as a wave, and had already succeeded in explaining a remarkable range of phenomena. But Compton found something that fit naturally with the quantum idea that electromagnetic radiation could exchange energy and momentum in photon-like units. He directed high-energy radiation at material containing electrons and examined the radiation that emerged after scattering. The scattered radiation did not always retain the same wavelength. At particular scattering angles, its wavelength became longer. That detail mattered enormously. A longer wavelength corresponds to lower frequency. Lower frequency means lower photon energy. And because photon momentum is directly related to photon energy, the scattered photon also emerged carrying less momentum than before. The electron, meanwhile, recoiled. The interaction could therefore be understood as an exchange in which both energy and momentum were conserved. The photon arrived carrying one amount of energy and momentum. It left with less energy, less momentum, and a different direction. The electron carried away the difference. This phenomenon became known as the Compton effect. It provided powerful evidence that photons possess momentum in their interactions with matter. The result was difficult to explain by treating the incident radiation only as a smooth classical wave transferring energy continuously across the material. The quantum description, by contrast, allowed the event to be treated as an interaction between a photon and an electron in which energy and momentum were both carefully conserved. That does not mean every kind of scattering should be pictured as a tiny photon colliding with a tiny electron in exactly the same simple way. Different scattering processes arise under different conditions. Rayleigh scattering, for example, becomes important when light interacts with particles or structures much smaller than its wavelength. In that case, the incoming electromagnetic field disturbs charges within matter, and those charges then radiate. For visible light travelling through Earth's atmosphere, Rayleigh scattering is one reason shorter wavelength light is scattered more strongly than longer wavelength light. That contributes to the familiar blue appearance of the daytime sky. The physics involved is not identical to Compton scattering. In Rayleigh scattering, the radiation can be scattered without the same kind of significant energy loss that characterizes Compton's scattering from electrons. But the momentum principle still applies. If light enters travelling in one direction and leaves travelling in another, its momentum has changed. The material involved in the scattering receives the balancing change. On the scale of one photon and one atom, that transferred momentum may be almost unbelievably small. A single visible photon carries an exceedingly tiny amount of momentum, but nature rarely provides just one photon. A bright beam contains an enormous flow of them. Sunlight striking matter involves vast numbers of interactions every second. Laser beams can concentrate electromagnetic energy into small regions. Around stars, intense radiation can continually scatter from atoms, ions, electrons, molecules, and dust. Tiny momentum changes begin to accumulate. A dust grain floating near a luminous star may scatter radiation from countless photons over long periods. Gas in a stellar atmosphere can interact with enormous flows of radiation. Electrons in a plasma can scatter higher energy photons and exchange both energy and momentum with them. Even the atmosphere around Earth is constantly redirecting incoming electromagnetic radiation. The exact outcome depends on the wavelength, the material, the energy of the particles involved, and the geometry of the interaction, but the conservation laws remain unchanged. The incoming radiation carries energy and momentum. The outgoing radiation carries energy and momentum. Matter carries energy and momentum as well. The totals must balance. This is why scattering can produce forces without anything resembling a conventional solid collision. An atom does not need to be struck by a massive projectile. A dust grain does not require a stream of microscopic material bullets. An electron can change its motion simply because the electromagnetic radiation interacting with it changes its own energy or direction. Seen this way, absorption, reflection, and scattering are not really three unrelated ways for light to push. They are three versions of the same deeper process. With absorption, the incoming radiation disappears into the material and transfers its momentum. With reflection, the radiation reverses or strongly changes direction, producing an even larger momentum change. With scattering, the radiation leaves in some new direction, and sometimes with a different energy, transferring whatever momentum is required to keep the entire interaction balanced. In every case, light arrives carrying momentum. Something happens to that momentum. and matter responds. The push may be unimaginably small in a single interaction, but repeated enough times and massless light can move atoms, grains of dust, clouds of gas, and eventually objects large enough for us to see. Once light is known to carry momentum, an unusual possibility appears. Instead of merely observing light pushing matter, physicists can deliberately use that push to control motion. This becomes especially useful when the objects being moved are atoms. An atom has a tiny mass, so the momentum delivered by a single photon, although extremely small by everyday standards, can make a measurable difference to its motion. If the process is repeated many thousands or millions of times, carefully directed light can slow atoms dramatically. This is the basic idea behind laser cooling. The word cooling can be slightly misleading at first. The lasers are not simply chilling atoms in the way a refrigerator cools food. Temperature is closely related to random microscopic motion. In a gas at an ordinary temperature, atoms are moving rapidly in many different directions. Some travel one way, others another, and their velocities are spread across a broad range. Reducing that random kinetic motion means reducing the temperature. Laser cooling therefore works by using the momentum of light to slow the atoms themselves. An important ingredient is the Doppler effect. The Doppler effect changes the frequency of a wave as perceived by an observer moving relative to the source. It is familiar from sound. An approaching siren sounds slightly higher in pitch, while the same siren moving away sounds lower. Atoms experience an analogous effect with light. Atoms absorb particular frequencies of electromagnetic radiation corresponding to transitions between their allowed energy states. These frequencies can be extremely precise. Suppose a laser is tuned to a frequency slightly lower than the frequency an atom normally absorbs. An atom sitting still may therefore be unlikely to absorb that light. But now imagine that the atom is moving toward the laser beam. Because of the Doppler effect, the light appears slightly shifted toward a higher frequency from the atom's perspective. If the atom is moving toward the beam at the right speed, that shifted frequency can match the atom's resonance. The atom then absorbs a photon, and because that photon was travelling opposite to the atom's motion, the photon transfers momentum that slows the atom slightly. The change from one photon is minute, but another photon can arrive, then another, then thousands more. Repeated absorption gradually reduces the atom's motion in that direction. This idea became the basis for powerful methods of laser cooling developed during the late 20th century. Stephen Chu, Claude Cohen-Tanucci, and William Daniel Phillips played major roles in advancing techniques for cooling and trapping atoms with laser light. Their work was recognized with the Nobel Prize in Physics in 1997. One particularly elegant arrangement became known as optical molasses. The name is rather descriptive. Imagine atoms surrounded by laser beams travelling in opposite directions along several axes. An atom moving to the right sees the beam coming from the right Doppler shifted closer to resonance. It therefore tends to absorb more photons from the direction it is moving toward. Those photons carry momentum pointing back toward the centre. An atom moving left encounters the same effect from the opposite beam. Similar pairs of beams act in the other directions. The result is a velocity-dependent force that resists the motion of the atoms. They begin to behave as though they are trying to move through something thick and sticky. There is, of course, no actual molasses present, which is fortunate for anyone hoping to keep a precision physics laboratory reasonably tidy. The slowing comes entirely from photon momentum. After an atom absorbs a photon, it usually does not remain permanently in the excited energy state. It eventually returns to a lower energy state and spontaneously emits another photon. That emitted photon also carries momentum. At first, this might seem to undo the cooling. If the atom absorbs momentum from one photon and then recoils when it emits another, perhaps the effects should simply cancel. But spontaneous emission occurs in effectively random directions. Over many emission events, those recoil directions largely average out. The absorption events, by contrast, are directionally biased, because the lasers have been arranged so that atoms moving in a particular direction preferentially absorb photons opposing their motion. The result is a net reduction in the atom's average velocity. This allows matter to be cooled to astonishingly low temperatures. Laser cooling can routinely bring atomic gases to temperatures far below 1 Kelvin. Depending on the technique and the atoms involved, temperatures can reach the microkelvin range, meaning millionths of a Kelvin above absolute zero. More advanced cooling methods can push certain systems even lower. At such temperatures, the random motion of the atoms becomes extraordinarily slow compared with ordinary gases. That opens the door to experiments that would otherwise be almost impossible. Laser-cooled atoms are used in some of the most precise atomic clocks ever constructed. When atoms move more slowly, Doppler shifts and other motion-related effects can be reduced, allowing their internal transitions to be measured with exceptional accuracy. Cold atoms are also important in precision measurements of gravity, rotation, fundamental constants, and tiny forces. They provide controlled environments for studying quantum mechanics on scales where delicate quantum effects would normally be blurred by thermal motion. Laser cooling also helped make possible the creation and study of unusual states of matter such as Bose-Einstein condensates, where atoms cooled to extremely low temperatures begin behaving collectively in striking quantum ways. The remarkable thing is that all of this depends on something that initially seemed almost contradictory. Light has no rest mass, yet it can slow an atom. It can remove kinetic energy from a gas. It can help produce some of the coldest controlled matter humans have ever created. And it does so because each photon arrives carrying momentum. One photon produces almost nothing noticeable. A carefully arranged stream of photons, interacting again and again with atoms, becomes a remarkably precise mechanical tool. Light is not merely something we use to see matter. Under the right conditions, it can reach into the motion of matter itself and gently bring it almost to rest. Light can do something even stranger than slowing matter down. Under the right conditions, it can hold matter in place. At first that sounds almost contradictory. Radiation pressure tends to push objects in the direction the light is travelling. So how can a beam of light trap a particle instead of simply nudging it away? The answer comes from shaping the light very carefully. The physicist Arthur Ashkin spent decades exploring how laser beams could move and control microscopic objects. His work eventually led to the development of optical tweezers, a technique in which a tightly focused beam of light can trap tiny particles near the region of highest intensity. The name is wonderfully literal. Instead of gripping something with metal tips, optical tweezers use light itself as the holding mechanism. The key is that a focused laser beam is not equally bright everywhere. Its intensity is greatest near the center of the focus and falls away toward the edges. This variation in intensity creates what is known as a gradient force. Consider a small transparent particle placed slightly away from the center of the beam. Light passing through one side of the particle may be more intense than light passing through the other side. Because the particle changes the direction of the light through refraction, the light's momentum changes. And whenever the momentum of light changes, the particle must receive a corresponding momentum change in return. The result can be a force drawing the particle toward the brighter central region of the beam, This is the gradient force. At the same time, there is another effect. Photons scattering from or passing through the particle can transfer momentum in the general direction the laser beam is travelling. This creates what is often called the scattering force. The scattering force tends to push the particle along with the beam. The gradient force can pull the particle toward the region of highest intensity. If the laser is focused strongly enough and the conditions are right, the gradient force can overcome the tendency of the scattering force to push the object away. The particle then settles near a stable position close to the focus. It has been trapped by light. Nothing solid surrounds it. There is no microscopic hook or clamp. The object is held because the electromagnetic field has been arranged so that small movements away from the equilibrium position produce forces tending to bring it back. The trap is not perfectly motionless. Microscopic particles in a fluid still experience random collisions with surrounding molecules. Thermal motion continually shakes them around, but the optical forces can confine them within a very small region, allowing researchers to manipulate them with remarkable precision. The objects involved can be extremely small. Optical tweezers can trap microscopic dielectric beads, tiny droplets, biological cells, and under suitable conditions individual atoms and other particles. This opened up possibilities far beyond simply demonstrating that light can exert force. Researchers discovered that a trapped microscopic bead could act like an extraordinarily delicate handle. Suppose a tiny bead is attached to a biological molecule such as deoxyribonucleic acid. If the bead is held in an optical trap, small forces acting on the molecule can pull the bead away from the center of the trap. By measuring that displacement, researchers can infer the force. The optical trap effectively becomes a microscopic force meter. This has allowed scientists to study forces on scales far below anything accessible with ordinary mechanical instruments. Individual strands of deoxyribonucleic acid can be stretched. Proteins can be manipulated. The motion of molecular motors can be observed one tiny step at a time. These molecular motors are biological structures that convert chemical energy into mechanical motion inside living cells. Some carry material along cellular tracks. Others help move or organize molecules. Their forces are incredibly small, often measured in piconewtons, meaning trillionths of a newton. Optical tweezers are sensitive enough to explore motion on this scale. Arthur Ashkin's pioneering work on optical trapping was eventually recognized with part of the Nobel Prize in Physics in 2018, particularly for the development of optical tweezers and their application to biological systems. The achievement is a beautiful demonstration of how a seemingly weak property of light can become an exceptionally powerful scientific tool. There is also an important conceptual point hidden inside the trap. At first glance, optical tweezers might appear to conflict with the simple statement that radiation pressure pushes objects away from a light source. But there is no contradiction. The force produced by light depends on how the electromagnetic field is arranged and how momentum is redirected during the interaction. A focused beam has a complicated spatial structure. Light approaches the particle from slightly different directions across the beam. The particle refracts, scatters, and redirects that light. Each small redirection changes the momentum of the electromagnetic radiation. The particle receives the balancing momentum changes. When all of those contributions are added together, the resulting force can point toward the center of the beam rather than simply forward. So the trapping force is still fundamentally about momentum transfer. It is simply a more carefully engineered version of it. This makes optical tweezers one of the clearest demonstrations that momentum carried by massless light can be controlled with extraordinary precision. The light can push, it can slow, it can pull a suitable particle toward a region of greater intensity. And with the right geometry, it can hold that particle almost motionless, while scientists examine forces millions or trillions of times smaller than the ones familiar in everyday life. The scale may be microscopic, but the principle is universal. Every force in the optical trap comes from changes in electromagnetic momentum, and once such a tiny force can be turned into a useful tool in a laboratory, there is no reason the same basic physics must remain confined to microscopic objects. In space, where resistance is extremely small and light can keep pushing for enormous stretches of time, the same gentle momentum transfer can be applied to objects vastly larger than anything held inside an optical trap. A spacecraft usually moves by throwing something in the opposite direction. A chemical rocket burns propellant and expels hot gas through its engines. The gas rushes one way, and the spacecraft gains momentum in the other. This is one of the clearest examples of conservation of momentum in action. But a solar sail offers a much stranger possibility. Instead of carrying large amounts of propellant, it can use sunlight itself. A solar sail is typically designed as a very large, extremely lightweight reflective sheet. Sunlight strikes the surface, changes direction as it reflects, and transfers momentum to the sail. The force is tiny. But it is continuous. Each individual photon carries only a minute amount of momentum. When enormous numbers of photons strike the sail every second, their combined effect produces a steady pressure. If the sail reflects much of the incoming sunlight, the momentum transfer is greater than it would be for simple absorption, because the outgoing radiation reverses much of its direction. The result is a small acceleration of the spacecraft. Compared with the thrust from a conventional rocket engine, this acceleration can seem almost insignificant. A rocket may produce an enormous force for minutes at a time. A solar sail may experience only a very gentle push. But there is an important difference. A rocket carries fuel. As that fuel is consumed, the available propellant runs out. A solar sail does not need to expend onboard reaction mass in order to receive its push from sunlight. As long as sufficiently intense radiation continues to strike the sail, the force can continue. That makes time extremely important. In interplanetary space, there is very little resistance to motion. A spacecraft does not have to fight its way through thick air, and there is no road surface producing friction beneath it. So a small acceleration does not need to overcome much drag. It simply keeps changing the spacecraft's velocity. The increase during 1 second may be tiny. After an hour, it may still be modest. But over weeks or months, those small changes accumulate. Given enough time, a gentle continuous force can produce a substantial difference in speed and trajectory. This idea has already been demonstrated beyond the laboratory. In 2010, the Japan Aerospace Exploration Agency launched a spacecraft called Interplanetary Kitecraft, accelerated by radiation of the Sun. The unusually long name was chosen so that its shortened form became the name Icaros. The spacecraft deployed a large, thin solar sail while travelling through interplanetary space. Sunlight exerted radiation pressure on that sail and produced a measurable change in the spacecraft's motion. Interplanetary Kitecraft, accelerated by radiation of the Sun, became the first spacecraft to successfully demonstrate solar sailing during an interplanetary journey. It showed that radiation pressure was not merely something that existed in equations or delicate laboratory experiments. It could be used as propulsion. Another important demonstration came from the Planetary Society. Its LightSail 2 spacecraft was launched in 2019 and deployed a reflective sail while orbiting Earth. By adjusting the sail's orientation relative to the Sun during different parts of its orbit, The mission demonstrated controlled changes in the spacecraft's orbital motion using sunlight. This reveals an important feature of solar sailing. A sail is not simply doomed to be pushed directly away from the sun. The force depends on the orientation of the sail. If the reflective surface faces sunlight directly, the momentum transfer acts largely outward from the sun. Tilt the sail, however, and the direction of the reflected light changes. Because the outgoing photons carry momentum in a different direction, the force on the sail changes direction as well. By controlling the angle of the sail, a spacecraft can change the way radiation pressure alters its orbit. This makes solar sailing a genuine form of navigation rather than a simple cosmic shove. The available force does change with distance. Sunlight becomes weaker as it spreads outward from the sun. The intensity follows approximately an inverse square relationship. If the distance from the sun is doubled, the same solar power has spread across roughly 4 times the area, so the intensity falls to about 1/4 of its previous value. At 3 times the distance, it falls to about 1/9. A solar sail therefore receives its strongest push close to the sun, and progressively less as it travels farther away. That limitation has inspired another far more ambitious idea. Instead of relying on sunlight, a sail could in principle be pushed by an artificial beam. A sufficiently powerful laser could direct electromagnetic radiation toward an extremely light reflective sail. The basic physics would remain the same. Photons would strike the sail, change momentum, and transfer some of that momentum to the spacecraft. But the source of the light would now be engineered rather than natural. Proposals for laser-driven light sails have explored the possibility of accelerating exceptionally small spacecraft to speeds far beyond those achieved by conventional probes. Such concepts remain technically demanding, requiring enormous laser power, precise beam control, exceptionally light sails, and solutions to difficult engineering problems. But none of the underlying propulsion physics requires a new kind of force. It is still radiation pressure. That is what makes the solar sail such a useful answer to the original puzzle. There is no massive stream of material flying from the sun and striking the sail. The sun certainly emits particles as part of the solar wind, but solar sailing is specifically based on electromagnetic radiation rather than that stream of matter. No onboard engine needs to throw propellant backward to create the sunlight-driven force. The electromagnetic radiation already arrives carrying momentum. The sail simply changes that momentum. When sunlight reflects, the outgoing light leaves carrying momentum in a new direction. Conservation of momentum requires the spacecraft to receive the corresponding change. A massless photon pushes a massive spacecraft not because it secretly contains conventional mass, but because rest mass was never the requirement. Momentum was. And given a large enough sail, a reflective enough surface, and enough time, even the almost imperceptible pressure of sunlight can become a method of travelling through the solar system. The push of light can move microscopic particles, hold atoms in place, and even alter the trajectory of a spacecraft. But around a star, the same effect is multiplied on an almost unimaginable scale. A star does not produce a narrow laboratory beam or a gentle stream of sunlight falling across a sail. It releases an enormous amount of electromagnetic energy in every direction, continuously, for millions or billions of years, and all of that radiation carries momentum. For a star like the Sun, the total power flowing outward is roughly 400 septillion watts. That energy moves through the stellar interior, eventually reaches the surface, and escapes into space as electromagnetic radiation. Most of the time, we think about this radiation simply as the light and heat produced by a star. but the escaping photons also exert forces. Inside a star, matter is held inward by gravity. Every layer is attracted toward the enormous amount of mass beneath it, so without some balancing effect, the star would collapse inward. The resistance to gravity comes from pressure within the stellar material. In a star such as the Sun, gas pressure plays a major role. The interior is extremely hot, and particles move rapidly, producing pressure that helps support the material above them. Radiation contributes as well. Photons travelling through the dense interior interact repeatedly with charged particles. They may be absorbed, emitted, and scattered countless times before energy finally reaches the surface. Each interaction can transfer momentum. The resulting radiation pressure acts as part of the outward support against gravity. For the Sun, radiation pressure is not the dominant source of support through most of the star. In much more massive and luminous stars, however, its importance increases dramatically. Very massive stars generate extraordinary amounts of energy in their cores. Their luminosities can reach hundreds of thousands or even millions of times the luminosity of the Sun. With that enormous flow of radiation comes an enormous flow of momentum. At some point, the outward force produced by radiation can begin competing seriously with gravity. The physicist Arthur Stanley Eddington helped formalize this balance during the early 20th century. The resulting concept is known as the Eddington luminosity. The Eddington luminosity is the approximate luminosity at which the outward force produced by radiation on ionized matter balances the inward gravitational attraction of a central object under a particular set of assumptions. In its simplest form, the calculation often considers fully ionized gas in which photons interact mainly through scattering by free electrons. The electrons receive momentum from the radiation. Because electrons are electromagnetically coupled to positively charged ions, the surrounding plasma responds as a whole. Gravity pulls the material inward. Radiation pushes it outward. At the Eddington luminosity, those effects can balance. This is not a rigid universal boundary that every real star encounters in exactly the same way. The actual behaviour depends on geometry, composition, opacity, magnetic fields, rotation, and the detailed ways radiation interacts with matter. But the Eddington limit provides an extremely useful scale. It tells us roughly how bright an object can become before radiation begins having profound dynamical effects on the surrounding material. As a luminous star approaches such conditions, photons are no longer merely escaping peacefully into space. They can help drive matter away. Massive stars often produce powerful stellar winds. These winds consist of material leaving the stellar atmosphere at high speeds, sometimes reaching thousands of kilometers each second. Radiation can play a central role in accelerating that material. One particularly important mechanism involves spectral lines. Atoms and ions do not interact equally strongly with every wavelength of light. They possess specific electronic transitions that allow them to absorb photons at particular frequencies. In the atmosphere of a hot massive star, ions can absorb stellar radiation through many of these spectral lines. Every absorbed photon transfers momentum. The ion is pushed slightly outward. Because enormous numbers of photons interact with enormous numbers of ions, the accumulated effect can drive a substantial flow of material away from the star. This process is known as line-driven acceleration. As the gas moves outward, the Doppler effect shifts the frequencies seen by the moving ions. That allows different parts of the outflow to interact efficiently with different portions of the stellar spectrum, helping the wind continue accelerating. The result can be dramatic. Over its lifetime, a very massive star can lose a significant fraction of its original mass through stellar winds. That lost material does not simply disappear. It enriches the surrounding interstellar environment with elements produced inside the star and alters the mass that remains when the star eventually reaches the later stages of its evolution. Light has therefore helped reshape the star that produced it. The same basic competition between radiation and gravity appears around compact objects. Gas falling toward a black hole, neutron star, or other dense object can release enormous amounts of energy as it forms a hot accretion flow or accretion disk. The resulting radiation can be extraordinarily intense. As photons move outward through surrounding gas, they transfer momentum through scattering and absorption. If the radiation becomes powerful enough, it can oppose continued infall and contribute to winds or other outflows from the accreting material. Once again, the Eddington luminosity provides an important reference point for understanding the balance between inward gravity and outward radiation force. This is an extraordinary change of scale. In a laboratory, photon momentum can move a microscopic bead. Near Earth, sunlight can slowly accelerate a reflective sail. Around a luminous star, radiation can help lift vast quantities of plasma out of a gravitational field and send them streaming into space. The individual photon has not changed. It still has zero rest mass. It still carries energy and momentum according to the same laws. What changes is the number of photons and the amount of energy flowing through the system. A single photon transfers almost nothing on an astronomical scale. A star releases an immense torrent of them every second. Together, their momentum can become powerful enough to influence the structure of stellar atmospheres, drive enormous winds, and compete with gravity itself. Massless radiation does not merely illuminate stars. Under the right conditions, it helps shape them. The push of light does not stop at the surface of a star. Once radiation escapes into space, it continues carrying momentum with it, and that momentum can influence almost anything capable of absorbing, reflecting, or scattering the light. In planetary systems, some of the clearest examples involve dust. A grain of cosmic dust may be tiny compared with a planet or spacecraft, but that small size can actually make radiation pressure unusually important. The reason is not simply that the grain is light, it is the relationship between its mass and the amount of surface area exposed to incoming radiation. A small particle can present a relatively large area to starlight while containing very little mass. That means even a modest force from radiation can produce a noticeable acceleration. For a larger object, gravity may overwhelmingly dominate. For a tiny grain, the contest can become much closer. Around the Sun, dust particles are pulled inward by gravity while sunlight pushes outward through radiation pressure. Both effects weaken with distance in roughly the same inverse square manner, because sunlight spreads outward while the gravitational field also falls with the square of distance. This means the balance between the two depends strongly on the properties of the grain itself. Size matters. Composition matters. Shape matters. The way the particle absorbs and scatters different wavelengths of light matters as well. For some grains, gravity comfortably wins. For others, radiation pressure becomes strong enough to alter the orbit substantially. Very small particles can even be pushed outward from the inner solar system. This competition between light and gravity appears dramatically in comets. As a comet approaches the Sun, its frozen materials begin releasing gas and dust. The material forms an expanding atmosphere around the nucleus and develops the long tails that make comets so visually distinctive. But there are usually different tails produced by different physical processes. The dust tail contains small solid particles released from the comet. These grains still feel the sun's gravity, but they are also pushed by radiation pressure. Because different grain sizes respond differently, the dust does not simply form a perfectly straight line pointing away from the sun. The particles retain some of their original orbital motion, while sunlight gradually changes their trajectories. The result is often a broad, curved dust tail. The ion tail is different. Gas molecules released from the comet can be ionized by solar radiation, producing charged particles. Those ions interact strongly with the solar wind and the magnetic field carried outward through the solar system. As a result, the ion tail tends to point much more directly away from the sun. It is useful to keep the distinction clear. Radiation pressure plays a major role in shaping the dust tail. The ion tail is governed mainly by charged particle interactions with the solar wind and magnetic fields. Even within the dust population, the effects of light can be surprisingly complex. Radiation pressure can gradually sort particles according to size and optical properties. Some grains remain in bound orbits. Some acquire substantially altered trajectories. Others can be driven outward. Over long periods, these effects help shape the distribution of fine material around stars. But sunlight can also produce a more subtle effect that seems at first almost opposite to the outward push of radiation pressure. It is known as the Poynting-Robertson effect. Consider a dust grain orbiting the sun. From the grain's own moving perspective, the sunlight does not appear to arrive from exactly straight ahead in the simple radial direction, because the grain itself is travelling sideways along its orbit. As the grain absorbs sunlight and later re-emits energy as thermal radiation, the complete momentum exchange produces a small drag on its orbital motion. The effect gradually removes angular momentum from the grain. Instead of being pushed steadily outward, the particle can slowly spiral inward toward the sun. This does not contradict ordinary radiation pressure. The outward radial force and the Poynting-Robertson effect are different components of the same broader interaction between moving matter and electromagnetic radiation. One mainly changes the radial balance between gravity and radiation. The other gradually changes the particle's orbital momentum. For an individual dust grain, these processes can operate over very long timescales. But across an entire planetary system, countless grains experience them continuously. Light, therefore, helps determine where fine material can remain, how long it survives in particular orbits, and whether it drifts inward or is pushed outward. The same principle becomes even more powerful around stars much brighter than the sun. Young stars can be surrounded by disks of gas and dust from which planets may form. Radiation from the central star can influence the small particles within those disks, particularly once the surrounding material becomes thin enough for starlight to penetrate efficiently. Around extremely luminous massive stars, the flow of photon momentum can be much stronger. Radiation can push directly on dust grains and interact with ions in surrounding gas. In some environments, the transfer of momentum from radiation helps drive powerful outflows. This connects to a broader idea in astrophysics known as feedback. An energetic object does not simply shine into its surroundings without consequence. The radiation it produces can influence the material around it. Photons can heat gas, they can ionize atoms, and because they carry momentum, they can also push. In star-forming regions, radiation from young massive stars can help reshape nearby clouds of gas and dust. In the neighborhood of intensely luminous objects, radiation pressure can contribute to moving material outward and changing the conditions under which gas continues to gather or collapse. The exact importance of radiation pressure varies greatly from one environment to another. Gravity, magnetic fields, gas pressure, stellar winds, and other processes may all be involved, but the role of light remains physically distinct. Whenever electromagnetic radiation is absorbed, scattered, or redirected, momentum is exchanged. The scale can be almost absurdly small. A single dust grain may receive a force too weak for any human sense to detect. Yet the grain itself is also tiny. The force can act for years, and there may be trillions upon trillions of similar grains experiencing the same underlying physics. That is how light becomes capable of shaping matter across space, not because photons suddenly gain rest mass when they leave a star, not because radiation somehow turns into an invisible wind of ordinary particles. The light continues to be electromagnetic radiation. It continues to carry energy and momentum, and wherever that momentum is transferred, matter responds. From a speck of dust drifting through the solar system to enormous clouds surrounding young and massive stars, massless light can quietly alter the structure of its environment simply by continuing to push. At the deepest useful level, the answer to how light pushes matter is surprisingly simple. Modern physics does not require something to possess rest mass in order for it to carry energy and momentum. That is the mistake hidden inside the original puzzle. We are used to massive objects doing the pushing. A hand moves a door. A hammer drives a nail. A moving ball strikes another ball and sends it rolling away. But nature is not limited to that familiar picture. Electromagnetic radiation can carry momentum through empty space, and when that momentum changes during an interaction, matter must respond. Quantum electrodynamics gives the modern quantum description of how this happens. Quantum electrodynamics is the quantum field theory describing interactions between electrically charged matter and the electromagnetic field. Its development emerged from the work of several physicists during the first half of the 20th century. Paul Adrian Maurice Dirac provided some of the earliest foundations by combining quantum mechanics with special relativity in a successful description of the electron. Later, Shinichiro Tominaga, Julian Seymour Schwinger, and Richard Phillips Feynman developed powerful methods for calculating electromagnetic interactions with extraordinary precision. Freeman John Dyson then helped show how these apparently different approaches were mathematically connected. The resulting theory became one of the most accurately tested frameworks in all of physics. Within this description, the photon is not best imagined as a tiny solid object made from some hidden substance. A photon is a quantum excitation of the electromagnetic field. The electromagnetic field exists throughout space, and its quantum excitations are what we identify as photons. That does not mean photons are unreal. They can transfer precise amounts of energy and momentum, they can be emitted and absorbed, they can scatter from charged particles, they can be detected individually under the right conditions. But picturing them as miniature balls made of material can lead us straight back into the misconception that something must possess ordinary mass before it can push. The more accurate picture begins with fields. Electrons are excitations of an electron field. Other particles are associated with their own quantum fields. The electromagnetic field interacts with electrically charged quantum fields. When light meets matter, the interaction ultimately involves these fields exchanging energy and momentum. A solid mirror, for example, contains enormous numbers of atoms. Those atoms contain electrically charged components, particularly electrons and positively charged nuclei. When electromagnetic radiation reaches the material, its electric and magnetic fields interact with the charged particles inside it. The collective response of those charges determines whether the radiation is absorbed, reflected, transmitted, or scattered. Whatever the detailed outcome, the complete interaction must obey conservation laws. energy is conserved. Momentum is conserved. If the momentum carried by the radiation changes, an equal and opposite accounting must appear elsewhere in the total system. That is the source of the force. The photon does not need to leave behind some tiny quantity of hidden mass. Nothing material has to leak out of the electromagnetic field and become attached to the mirror. The momentum transfer is enough. Relativity provides an even broader way of seeing why this is natural. In general relativity, the gravitational influence of something is not determined only by rest mass. The central mathematical object is known as the stress energy tensor. The name can sound rather formidable, but conceptually it collects several closely related physical properties. It describes energy density. It describes momentum density. It includes the flow of energy and momentum. It also contains pressure and stress. This matters because it reveals that pressure is not some secondary curiosity added onto the physics of energy. Pressure and momentum flow are deeply connected. Electromagnetic radiation carries energy through space. It carries momentum through space, and that moving energy and momentum form part of the stress energy content of the universe. This is also why light can contribute to gravity. A beam of light has no rest mass, yet it contains energy and momentum. General relativity responds to that broader stress energy content rather than only to the rest mass of material objects. So radiation can both be influenced by gravity and contribute, in principle, to the gravitational field. For ordinary beams of light, this gravitational contribution is fantastically small, but conceptually it is important. It reinforces the same lesson from a completely different direction. Rest mass is not the only physical quantity capable of producing real effects. Energy matters, momentum matters, pressure matters, stress matters, and electromagnetic radiation possesses several of these despite having zero rest mass. This also allows the classical and quantum descriptions of light to fit together. James Clerk Maxwell's electromagnetic theory describes light as a propagating electromagnetic field. That field carries energy and momentum. When it interacts with matter, the momentum flow produces radiation pressure. Quantum electrodynamics describes the same electromagnetic field in quantum terms. Its excitations are photons, and individual photons carry quantist amounts of energy and momentum. Special relativity explains why those photons can have zero rest mass while still possessing both. These are not three incompatible stories. They are descriptions of the same physics viewed at different levels, at large scales, where enormous numbers of photons are involved. The classical electromagnetic field can often describe radiation pressure beautifully. At the scale of individual interactions, the quantum picture becomes essential, and underneath both lies the relativistic relationship between energy and momentum. Nothing in that framework requires us to imagine that photons secretly possess conventional mass. In fact, giving photons even a tiny non-zero rest mass would alter electromagnetism in ways that experiments have never required. The clean description is the one physics already gives us. Photons are massless excitations of the electromagnetic field. They carry energy. They carry momentum. They interact with charged matter, and those interactions redistribute energy and momentum between the radiation and the material. That is what is really doing the pushing. When light is absorbed, its momentum is transferred. When light is reflected, its momentum changes direction, and the reflecting surface receives the difference. When light scatters, the outgoing radiation carries momentum in a new direction, and matter receives the balancing recoil. When a laser slows an atom, photon momentum is transferred again and again. When a solar sail accelerates, sunlight repeatedly changes direction from its reflective surface. When intense radiation drives gas away from a star, the same principle is operating on an astronomical scale. The scale changes enormously. The underlying physics does not. Light pushes because light carries momentum. And whenever an interaction changes the momentum carried by the electromagnetic field, conservation of momentum requires something else to change its momentum too. That something may be an electron, an atom, a grain of dust, a mirror, a spacecraft, or an enormous cloud of stellar gas. The photon does not need rest mass to make any of it happen. It only needs momentum. And according to relativity, electromagnetism, and quantum physics, that momentum was there all along. So if light has no mass, how can it push things? The answer is that light does not need rest mass in order to carry momentum. A photon has zero rest mass, but it still carries energy. And because energy and momentum are linked by relativity, a photon also carries momentum. Whenever that momentum is transferred to matter, the matter experiences a change in motion. That is the push. The confusion usually comes from the familiar Newtonian expression in which momentum is described as mass multiplied by velocity. For ordinary objects travelling far below the speed of light, that relationship works extremely well. But it is not the complete relativistic description of momentum. Light lives in a different regime. James Clerk Maxwell had already shown during the 19th century that electromagnetic waves could carry energy through space. His theory also implied that those waves carry momentum and should therefore exert radiation pressure when they interact with matter. That prediction was eventually tested directly. Pyotr Nikolaevich Lebedev measured the tiny mechanical pressure produced by radiation, while Ernest Fox Nichols and Gordon Ferry Hull carried out their own sensitive experiments, showing that light really could exert force on matter. The effect was small, but it was measurable. Then quantum physics deepened the picture. Max Carl Ernst Ludwig Planck introduced the idea that electromagnetic energy could be exchanged in discrete quantities. Albert Einstein later used that idea to explain the photoelectric effect, helping establish the quantum description of light that eventually became associated with photons. Each photon carries a definite amount of energy, and for a photon travelling through vacuum, the relationship is wonderfully simple. Momentum equals energy divided by the speed of light. There is no rest mass in that expression. A photon can therefore be massless while still carrying momentum perfectly consistently. What happens when the photon meets matter depends on the interaction. If the light is absorbed, its momentum is transferred into the material. If the light is reflected, its momentum changes direction, producing an even larger transfer. If it is scattered, its direction or energy changes, and the surrounding matter receives the corresponding change in momentum. Absorption, reflection, and scattering may look different, but underneath they are variations of the same principle. The momentum of the radiation changes. Matter responds. That single idea works across an extraordinary range of scales. Laser cooling uses repeated photon momentum transfers to slow atoms and reduce their random motion. Optical tweezers use carefully shaped laser fields to trap microscopic particles without physically touching them. Solar sails exploit reflected sunlight to produce a continuous force on spacecraft. Inside and around extremely luminous stars, radiation pressure can influence enormous quantities of gas and help drive stellar winds. Even tiny grains of cosmic dust can have their trajectories altered simply because starlight keeps transferring momentum to them. The physics does not change as the scale changes. At no point do photons need to acquire some hidden conventional mass. They remain massless excitations of the electromagnetic field. Their ability to exert force comes from energy and momentum, not from secretly behaving like tiny, massive projectiles. That is perhaps the deeper lesson hidden inside the original question. Our everyday intuition encourages us to connect pushing with weight, solidity, and mass because those are the interactions we experience most often. Nature is more subtle than that. Mass, energy, momentum, and force are related, but they are not interchangeable. Something can possess no rest mass at all and still carry real energy through space. That energy can come with momentum. And if the momentum changes, something else must receive the difference. So a beam of light may appear almost weightless and insubstantial. It can cross empty space without carrying ordinary matter with it. And yet when it finally reaches something, it can warm it, move it, slow it, steer it, or very gently push it away. Not because light secretly has mass, but because nature conserves momentum.